There is a photograph taken in 1947 that most people have never seen. It shows a glass chamber filled with vapor and a set of thin white lines curving through the mist. The lines are particle tracks, charged particles moving through the vapor trigger condensation along their path, the way a finger drawn through fog leaves a momentary trail. The device is called a cloud chamber, and by 1947 it had already been responsible for some of the most significant discoveries in particle physics. The positron was found in one. The muon was found in one. It was the sharpest instrument available for seeing particles that no human eye could otherwise detect. The particles leaving those tracks were not produced in a laboratory. They arrived from space. Cosmic rays, a continuous stream of high-energy particles from outside the solar system, strike the upper atmosphere constantly and produce cascades of secondary particles that shower downward toward the ground. George Rochester and Clifford Butler were capturing those cascades in a cloud chamber in Manchester, England. They had placed their chamber inside a magnetic field so that the curvature of each track would reveal the charge and momentum of whatever passed through. The cloud chamber works simply. A charged particle moving through supersaturated vapor ionizes the molecules along its path. Those ions become nucleation sites. Droplets form. The trail becomes visible. A camera captures it before it dissolves. The magnetic field bends the track, and the direction and degree of bending tell you everything you need to know. Which way it curves tells you the charge. How tightly it curves tells you the momentum. Light particles curve sharply. Heavy particles barely curve at all. By 1947, the known particle inventory was small, and the signature were well understood. Electrons left tight curling tracks. Protons left thick, nearly straight ones. Muons left clean, smooth curves. Photons left no track at all but announced themselves by converting into electron-positron pairs at a single point, producing a V-shape pointing in the direction the photon had been traveling. The physicists reading these photographs knew every signature. They had seen thousands of them, which is why when Rochester and Butler developed their photographs and looked carefully at what the cosmic ray cascade had left behind, they recognized immediately that something did not belong. There was a V shape in one of the images, but it was not the V of a photon converting into a pair. The tracks coming out of the vertex were wrong for that. The curvature was wrong. The angles were wrong. Whatever had produced that V had traveled some distance through the chamber without leaving any track of its own, which meant it carried no charge, and then decayed at a point into two charged particles that fanned outward. It had come from the cosmic ray shower above, and it was not anything physics had a name for. They sat with a photograph for a long time before publishing. The result was too strange to announce carelessly and too clear to dismiss. Something real had passed through their detector. It had left the signature of a particle that did not exist in any known inventory, and it had done so quietly, in a glass box in the north of England, while nobody was specifically looking for it. But the questions it left behind were impossible to ignore. If this particle was real, why did nothing in physics predict it? And if nothing predicted it, what else was the inventory missing? If you like exploring questions like these, feel free to leave a like and subscribe. And if there is something about the universe you find yourself wondering about now and then, let us know in the comments. It might become the next question we explore. For now, let's return to the topic. The photograph sat in the literature quietly for a few years. Then the accelerators turned on, and the quiet ended. The photograph showed a decay. That much was immediately clear. A neutral particle, carrying no charge and therefore leaving no trail of its own, had travelled a short distance through the chamber and then split into two charged particles that curved away from a common point. The geometry was clean. The two outgoing tracks formed a V, and the momentum carried by those tracks pointed back to a single parent. That parent had a definite mass. It was not a ghost or an artifact of the equipment. Something real had passed through the chamber, travelled a visible distance in silence, and then become two things at a precise point in space. The first task was to identify it. In particle physics, identifying an unknown particle means measuring everything the data will give you and comparing it against everything already known. Mass is the starting point. The momentum of the two outgoing tracks, combined with the angle between them and the known masses of the particles they belong to, allowed Rochester and Butler to calculate the mass of the parent. It came out to roughly half the proton mass. That placed it in a region of the mass spectrum that was not empty. Pions lived there, the particles Yukawa had predicted to explain the nuclear force, and that had been found in cosmic ray experiments just the year before. Could this be a pion decaying in an unusual way? No. The mass did not match any known pion decay. The decay products did not match either. When physicists worked through the numbers carefully, the two outgoing tracks were consistent with a proton and a pion emerging from a common point. A proton and a pion. That combination had a specific meaning. It meant the parent particle, whatever it was, had decayed into one particle that felt the strong force strongly, the proton, and one that felt it moderately, the pion. The decay was real, reproducible, and pointed unambiguously at a parent with a mass sitting between the pion and the proton, in a region no known particle occupied. Rochester and Butler called it a neutral V particle for the shape it left. Others called it a heavy meson, a neutral kaon, a theta particle. The naming conventions of the early 1950s were unsettled because the particle itself was unsettled, an object without a home in any existing framework. What eventually stuck, once the particle was more carefully characterized and distinguished from its relatives, was the name that has stayed ever since: the Lambda. A neutral baryon, heavier than a pion, lighter than a proton plus a pion combined, decaying cleanly into those two particles at a point that could be measured and reproduced. The mass was pinned down. The decay products were identified. The Lambda was real. It had a mass, and it decayed into a proton and a pion. What it was, and where it fit in the architecture of matter, was a question the existing framework had no answer for. The accelerators coming online in the early 1950s were about to make that question considerably more urgent. When the first particle accelerators came online in the early 1950s, physicists finally had something they had never had before: control. Cosmic ray experiments were patient work. You set up a detector, you waited, and occasionally something interesting fell through from above. You could not aim cosmic rays at a target and collect statistics on demand. Accelerators changed that entirely. You could produce collisions at will, at specific energies, and collect thousands of events where before you had dozens. The Lambda, which had appeared sporadically in cosmic ray photographs since 1947, now appeared constantly, reliably in collision after collision, and that reliability was itself a measurement. In particle physics, the rate at which a particle is produced in a collision is not a neutral observation. It is a fingerprint. Each of the fundamental forces has a characteristic strength, and that strength determines how often the processes it governs actually occur. The strong force is the most powerful of them. It acts on timescales around 1/70th of a second and produces interactions at rates that reflect that speed. When a high-energy collision governed by the strong force occurs, the particles that emerge do so prolifically and quickly. The strong force does not produce particles occasionally or reluctantly. When it acts decisively, and the results show up clearly in the data. Think of it like water pressure in a pipe. Low pressure produces a trickle. High pressure produces a torrent. The strong force is high pressure. Anything it produces in abundance. And the lambda was produced in abundance. Every time physicists ran high-energy proton collisions and looked at what came out, the lambda was there in numbers that match the strong force production rate precisely. Not approximately. Precisely. The strong force was making the lambda the way high pressure makes a torrent, copiously, consistently, and fast. That production rate established something important before a single lifetime measurement was made. It told physicists which force owned the lambda. The strong force made it. That was not an interpretation or an inference. It was written directly into the production rate, as clearly as a signature on a document. And once you know which force makes a particle, you know which force should destroy it. Because the coupling that makes a force effective at producing a particle is the same coupling that makes it effective at acting on that particle once it exists. The strong force does not selectively engage with particles during production, and then politely step aside afterward. If it is strong enough to make something, it is strong enough to unmake it. This is the expectation the lambda set up for itself, simply by appearing so frequently. It announced, through its own production rate, exactly how long it should survive. A particle produced at the rate the strong force produces the lambda should decay at the rate that the strong force decays everything else it touches. 1/70th of a second. It should be gone before it travels any distance a detector could measure. It should leave no track of its own, produce no visible trail, and decay so close to the collision point that distinguishing its decay products from the collision debris would be nearly impossible. That was the prediction, unambiguous, quantitative, and grounded in the same data that established the lambda's existence in the first place. The strong force made it. The strong force should destroy it. The timescale was fixed by the physics before anyone put it to the test. Then the lifetime measurement came back, and the number it returned was not 1/70th of a second. It was not close to 1/70th of a second. It was not in the same universe as 1/70th of a second. Measure the lambda's lifetime, and the number that comes back is wrong. Not slightly wrong. Not slightly wrong. Not wrong in a way that could be attributed to experimental error or an imprecise calculation. Wrong by a factor so large that it sits outside any reasonable margin of uncertainty and demands a structural explanation. The lambda lives for roughly 1/10th of a nanosecond before decaying. That sounds short. In everyday terms, it is essentially instantaneous. But in particle physics terms, it is an eternity. The strong force should have killed the lambda roughly 100 billion times faster than that. The gap between expectation and measurement is not a rounding error. It is a signal. To feel the weight of that gap, consider what it means for a particle to live 100 billion times longer than expected. Imagine predicting that a ball dropped from a building will hit the ground in 1 second, and then watching it take 3,000 years to arrive. The physics governing the fall has not changed. Gravity is still acting. But something is interfering with it, slowing it down, preventing it from doing what it should do at the rate it should do it. Whatever that something is, it is not a small correction. It is a dominant effect that has completely changed the outcome. That is the situation the lambda presented. The strong force was clearly capable of producing it. The production rate confirmed that beyond any doubt. But once the lambda existed, the strong force appeared unable to destroy it at anything close to its normal pace. Something was suppressing the decay. Something was preventing the strong force from acting on the lambda the way it acted on every other particle it had ever been observed to act on, and that something left no other trace in the data. It did not show up in the production process. It did not affect the lambda's mass or charge or any other measurable property. It only showed up in the lifetime, written as an absence, as a decay that should have happened and didn't. The decay the lambda eventually underwent made the situation stranger. When it finally decayed, it did so into a proton and a pion. Both of those are strongly interacting particles. The decay products felt the strong force. The lambda felt the strong force, at least during production. So why was the decay so slow? If the strong force connected the lambda to its decay products, the transition between them should have been fast. The strong force should have driven it. Instead, the timescale matched the weak force, the force responsible for radioactive decay, the force that operates billions of times more slowly than the strong force and governs processes like the decay of a neutron into a proton inside an unstable nucleus. The lambda was being created by one force and destroyed by another. Production and decay were following different rules, and in 1950, nobody had a framework that allowed for that. A particle was supposed to interact with a force or not interact with it. The idea that a particle could be fully subject to the strong force in one context and effectively invisible to it in another was not part of any existing theory. It required something new, not a small adjustment to existing ideas. Something genuinely new, a property that nobody had postulated, that the lambda appeared to carry and that governed when the strong force could act and when it could not. The data was not ambiguous. The lifetime was measured repeatedly and the answer was always the same. 1/10 of a nanosecond, 100 billion times too long. The lambda was not broken. Physics was incomplete, and the incompleteness had a very specific shape, defined precisely by the gap between what the strong force predicted and what the lambda actually did. That gap needed a name before it could be understood. There is a pattern in the accelerator data from the early 1950s that nobody had been looking for specifically, but that became impossible to ignore once the event counts grew large enough. Search through every collision event containing a lambda, and something else always appears in the same event. A kaon, every single time, not most of the time, not usually, every time. The lambda and the kaon were born together in the same collision without exception, and that exception-free pairing, once noticed, stopped looking like a coincidence very quickly. Think about what it would mean to flip a coin and have it land heads 100 times in a row. At some point, you stop attributing the result to chance and start looking for a physical explanation. The coin is weighted, the flip is controlled, something is enforcing the outcome. The lambda-kaon pairing had that character. The numbers were too consistent, the pattern too clean, to be the result of random chance. Something was enforcing it. The question was what? In physics, when a quantity is preserved without exception across every interaction you observe, the explanation is almost always a conservation law. Conservation laws are the universe's way of keeping accounts. Electric charge is conserved, meaning the total charge before a collision always equals the total charge after. Energy is conserved, momentum is conserved. These are not suggestions, they are absolute rules, and they are enforced in every interaction without exception. When you see a pattern as consistent as the lambda-kaon pairing, the first instinct of a physicist is to ask what quantity is being conserved that forces the pattern to hold. The answer the data pointed to was this. The lambda carried some property that ordinary particles did not carry. The kaon carried the opposite amount of that same property. Together, they summed to zero. The collision that produced them started with ordinary protons carrying none of this property, so it had to end with a total of zero as well. One lambda, one kaon, zero net balance. The book stayed balanced because both particles were created simultaneously, each one carrying the opposite sign of whatever this new property was. That explained production, but it also explained the lifetime, and this is where the two problems that had seemed separate suddenly collapsed into one. Once the Lambda existed on its own, travelling away from the collision point, it carried this property alone. The kaon was gone, moving in a different direction, eventually decaying in its own way. For the strong force to decay the Lambda quickly, it would need to produce final state particles that also balance the books. A proton and a pion, the Lambda's actual decay products, carried none of this property. The total would not be zero. The books would not balance. The strong force, which enforces this conservation law absolutely and without exception, could not complete that decay. Not because it was weak or suppressed or interfered with, but because doing so would violate its own accounting rules. It was blocked by the same principle that governed its behavior in every other interaction it had ever been observed to participate in. The Lambda was not an exception to the strong force. It was the strong force following its own rules so strictly that it could not finish what it had started. Two problems that had resisted explanation for years, the paired production and the long lifetime, had just collapsed into a single question. What was the property the Lambda carried that the strong force could not change? It had a shape now. It had a precise definition. It just needed a name. The property the Lambda carried needed a name, and the name Murray-Gell-Mann gave it in 1953 was Strangeness. Not as a vague descriptor, as a precise quantum number, a measurable quantity assigned to each particle, carried through interactions, and governed by specific rules about when it could change and when it could not. The Lambda carried strangeness -1. The kaon carried strangeness +1. Ordinary particles, protons, neutrons, pions carried strangeness 0. Those assignments were not arbitrary. They were chosen specifically to make the accounting work across every observed interaction, and once chosen, they held without exception across every experiment that followed. The rule Gell-Mann identified was this: the strong force conserves strangeness absolutely. In any interaction governed by the strong force, the total strangeness before the interaction must equal the total strangeness after. This is why the Lambda and the kaon were always produced together. A proton carrying a strangeness of 0 colliding with another proton carrying strangeness 0 produces a total strangeness of 0. To produce a Lambda with strangeness -1, the interaction must simultaneously produce something with strangeness +1 to keep the total at 0. The kaon with strangeness +1 was that something. The pairing was not a coincidence. It was the strong force enforcing its own accounting rules in real time. Think of it like a currency exchange with a strict policy. You walk in with 0 foreign currency, and you want to leave with some. The policy says the total foreign currency in the room must never change. The only way to leave with some is if someone else simultaneously takes on an equal and opposite amount. You cannot acquire strangeness alone. You can only acquire it if the universe simultaneously creates the opposite amount somewhere nearby, in the same interaction, at the same moment. The Lambda and the kaon were that transaction. One took on strangeness -1, the other took on strangeness +1. The total stayed 0. The policy was satisfied. That explained production completely. But the lifetime was the more elegant result. Once the Lambda existed alone, carrying strangeness -1, moving away from its kaon partner, the strong force faced an impossible accounting problem. To decay the Lambda into a proton and a pion, both carrying strangeness 0, the strong force would have to make strangeness -1 disappear. The books would go from -1 to 0. That is a change of 1 unit of strangeness. The strong force which never allows strangeness to change could not permit it, so it didn't act. It stood aside not because it was overpowered, but because its own rules blocked it. The weak force operates under different rules. It does not conserve strangeness. It can change strangeness by one unit in a single interaction, which is exactly what the Lambda decay requires. But the weak force is slow. It is slow because the particles that carry it are very massive, making the interactions they mediate rare and infrequent, and that slowness produced the Lambda's long lifetime directly and quantitatively. The lifetime was not a mystery anymore. It was the weak force's characteristic timescale, written into the Lambda's behavior, because the weak force was the only force with the authority to complete the decay. Strangeness did something that quantum numbers rarely do so cleanly. It took two separate experimental puzzles, the paired production and the long lifetime, that had resisted explanation for years, and dissolved both of them simultaneously with a single assignment. One number, one rule, two problems gone. That kind of economy is rare in physics. One number dissolving two separate mysteries simultaneously is not something you expect. It is the kind of result that makes you think the universe was hiding something obvious all along and waiting for someone to ask the right question. That is the signature of a correct physical idea, and Gell-Mann recognized it as such. Strangeness was not a patch applied to a broken theory. It was a revelation that the theory had been missing a layer, and that layer, once added, made everything that had seemed broken suddenly inevitable. But strangeness raised a question it could not answer by itself. If particles could carry this new property, how many particles carried it? And what determined how much strangeness each one had? By the mid-1950s, the accelerators were running continuously, and the particle inventory was growing faster than anyone could comfortably explain. Before the accelerators, the known particle list was short enough to fit on a single page. Protons, neutrons, electrons, pions, the muon, a handful of others. The cloud chamber photographs had added the lambda and the kaon, which was already two particles too many for the existing framework to accommodate comfortably. Then the accelerators started producing collisions at energies no cosmic ray experiment could match, and the list stopped being manageable. New particles arrived in batches, the sigma, a baryon like the lambda but carrying a charge, the psi, heavier and stranger still, the eta, the rho, the omega meson, the phi. Kaons came in multiple versions, charged and neutral, with subtly different behaviors. Each new particle had a mass, a charge, a lifetime, a set of decay products, and a strangeness value that had to be assigned carefully to make the accounting work. Each one required its own measurements, its own careful characterization, its own place in a catalogue that was expanding faster than anyone had anticipated when the accelerators were first designed. The situation felt less like discovery and more like accumulation. In science, accumulation without organization is a warning sign. When you find one anomalous object, you have an anomaly. When you find two, you have a pattern waiting to be identified. When you find dozens, all related, all sharing certain properties, while differing in others, you have a structure that is demanding to be understood. The particle zoo, as physicists began calling it, with a mixture of affection and exasperation, was not a random collection of unrelated objects. The particles in it were too similar to each other in too many ways for that. They clustered, they grouped, their masses fell into ranges that overlapped in suggestive ways. Their strangeness values were always integers, never fractions. Their charges followed patterns that repeated across different mass scales. Think of it the way early chemists must have felt before the periodic table existed. By the mid-19th century, dozens of elements had been identified, each with its own measured properties, its own atomic weight, its own characteristic reactions. The list was real, and the measurements were reliable, but without an organizing principle, it was just a catalogue. Mendeleev's insight was that the catalogue had a hidden structure, that the elements were not a random collection but a pattern, and that the pattern was regular enough to predict elements that had not yet been found. The particle zoo of the 1950s was at exactly that stage. The catalogue was real, the structure was hidden, and the measurements were precise enough that whoever found the organizing principle would be able to read it directly out of the data. The strangeness values were the first clue that the structure existed. Every particle in the zoo carried a strangeness value that was a whole number, and those values were not distributed randomly. They clustered around specific values in ways that grouped particles together. Particles with the same strangeness tended to have similar masses. Particles with different strangeness values were heavier in a direction that suggested a pattern. The clustering was not perfect, and the pattern was not immediately obvious, but it was there in the data for anyone who looked carefully enough and had the right mathematical language to describe what they were seeing. That mathematical language was about to arrive, and when it did, the zoo would stop looking like chaos and start looking like a map. The mathematical language that organized the particle zoo came from an unexpected direction, not from new experiments or new measurements, but from symmetry, specifically from the branch of mathematics that studies symmetry in its most abstract form, group theory, and from a symmetry group called SU3 that Gell-Mann and Israeli physicist Yuval Ne'eman identified independently in 1961 as the hidden organizing principle behind the hadron spectrum. Symmetry in physics is not just an aesthetic observation, it is a structural claim. When you say a system has a symmetry, you are saying that something about it remains unchanged under a specific transformation. A circle has rotational symmetry because rotating it by any angle leaves it looking identical. A square has a more restricted symmetry because only rotations by 90 degrees leave it unchanged. The more symmetry a system has, the more constrained its behavior, and the more predictive power you gain by identifying it. Symmetry is not decoration, it is architecture. What Gell-Mann noticed was that the hadrons, the strongly interacting particles filling the zoo, were not distributed randomly across the space defined by their charge and strangeness values. When you plotted them on a grid with electric charge on one axis and strangeness on another, they fell into specific geometric shapes. 8 particles of similar mass arranged themselves into a hexagonal pattern with 2 particles at the center. 10 particles of similar mass arranged themselves into a triangular pattern. The shapes were not approximate, they were exact, and they were the shapes that the mathematics of SU3 symmetry predicted a particle spectrum would take if that symmetry were governing the underlying physics. Think of it like finding that every painting in a gallery, regardless of subject or style, uses exactly the same set of 7 colors in exactly the same proportions. At first, you might think it is coincidence. Then you might think the painters were influenced by each other. But if the pattern holds across every painting without exception, including ones painted in different countries by artists who never met, you start to think the constraint is coming from somewhere deeper than individual choice. The pattern is being imposed by something outside the paintings themselves. The hadron spectrum had that character. The geometric arrangement of particles in charge strangeness space was too precise to be accidental. SU3 was not a description someone had imposed on the data after the fact. It was a structure the data was already expressing, waiting for the right mathematical lens to make it visible. Gell-Mann called the organizing scheme the Eightfold Way, a name borrowed from Buddhist philosophy that referred to the 8-member family of particles that exemplified the pattern most clearly, the octet of light baryons of which the Lambda was a member. The Lambda fit into the Eightfold Way exactly. Its charge, its strangeness value, and its mass placed it precisely where the SU3 symmetry required a particle to sit. It was not an outlier or an exception. It was a necessary member of a geometric family, its position in the pattern as fixed as the position of a note in a musical scale. The same was true for the sigma, the psi, the kaon, and every other strange particle that had been puzzling physicists since the early 1950s. Each one had a place. Each place was defined by the symmetry. And the symmetry, once you accepted it, was not just organizing the known particles. It was pointing at one that had not been found yet. There was a gap in the triangular pattern of 10 particles. A specific position in the geometry was empty, and the symmetry said it should not be. Whatever particle belonged there had a strangeness value of -3, a specific charge, and a mass the pattern allowed you to estimate before a single measurement was made. The Eightfold Way was not just a filing system, it was making a prediction. A prediction in physics is only as good as its specificity. A theory that predicts something will eventually be found somewhere is not really making a prediction at all. It is making a wish. A real prediction names the object, specifies its properties before the search begins, and puts itself at genuine risk of being wrong. The Eightfold Way did exactly that. The gap in the triangular pattern of 10 baryons was not vague, it was precise. The missing particle had to carry strangeness -3. It had to carry a specific electric charge of -1. And its mass, estimated from the pattern of masses already filling the other 9 positions in the triangle, had to come out near 1,680 mega-electron volts. Those 3 numbers were on the table before anyone went looking. The prediction was specific enough to be falsified, which is the only kind of prediction that means anything. The search began at Brookhaven National Laboratory in New York, where a bubble chamber the size of a small room was being used to photograph the products of high-energy particle collisions. A bubble chamber works on the same principle as a cloud chamber, but in reverse. Instead of vapor that condenses along a particle track, it uses a superheated liquid that boils along one. A charged particle moving through the liquid leaves a trail of tiny bubbles that can be photographed before they disperse. The images are denser and more detailed than cloud chamber photographs, and the liquid can be made dense enough to stop shorter-lived particles before they decay, giving physicists a chance to measure their properties directly rather than inferring them from decay products alone. In 1964, a team at Brookhaven led by Nicholas Samios was scanning through hundreds of thousands of bubble chamber photographs, looking for the specific signature the omega- would leave. The signature was not simple. A particle with strangeness -3 decaying through a chain of intermediate particles would produce a complex branching pattern in the image, a cascade of tracks, and secondary vertices spreading outward from a single origin point. The team knew exactly what that cascade should look like, because the Eightfold Way told them what the omega- would decay into, and in what sequence. They were not searching blindly, they were looking for a very specific shape in a very large pile of photographs. They found it. One image out of hundreds of thousands showed the precise cascade the prediction required. A particle appeared at a point with no incoming track, meaning it was neutral, travelled a short distance, and then decayed into a sequence of particles whose strangeness values decreased one step at a time, exactly as the weak force changing strangeness by 1 unit per decay would produce. The mass of the parent, calculated from the tracks of its decay products, came out at 1,672 mega-electron volts. The prediction had said 1,680. The charge was -1. The strangeness was -3. Every number matched. There is something quietly astonishing about that moment. A pattern drawn on paper in 1961 described a particle nobody had ever seen, specified its properties in advance, and turned out to be exactly right. That is not supposed to happen by accident. When mathematics reaches ahead of observation and lands correctly, it means the mathematics was touching something real. The omega minus was exactly where the Eightfold Way said it would be, with exactly the properties the symmetry had specified, found by people who knew precisely what they were looking for, because a mathematical pattern had told them where to look. That is not the signature of a filing system. A filing system organizes what already exists. It does not tell you what does not exist yet. The Eightfold Way had reached beyond the known data and correctly described something nobody had ever seen. That kind of predictive success means the symmetry is not being imposed on the particles from outside. It is emerging from something the particles actually share on the inside. The question that followed was unavoidable. What was on the inside? When a symmetry describes nature this precisely, the right response is not to admire it and move on. It is to ask what physical reality is producing it. The SU3 symmetry of the Eightfold Way was not a coincidence, and it was not a trick of the mathematics. It was a signal, and the signal was pointing inward, toward a layer of structure beneath the hadrons that nobody had directly observed, but that the pattern was making increasingly difficult to deny. Murray Gell-Mann and George Zweig reached the same conclusion independently in 1964, the same year the omega minus was found. If the hadrons were organized by SU3 symmetry, and if that symmetry was real rather than merely descriptive, then the hadrons could not be fundamental. They had to be built from something more basic, something whose properties combined in specific ways to produce the charge, strangeness, and mass patterns the Eightfold Way described. Gell-Mann called these constituents quarks. Zweig called them aces. The name quark stuck, borrowed from a line in James Joyce's Finnegan's Wake, and the objects it named were unlike anything physics had proposed before. 3 quarks were required, not 2, not 4. 3, because SU3 is the symmetry of 3. The mathematical structure of the group is built around transformations among 3 fundamental objects, and those 3 objects corresponded to 3 distinct quark types. Gell-Mann called them up, down, and strange. The up quark carried an electric charge of +2/3. The down quark carried -1/3. The strange quark carried -1/3 and additionally carried strangeness -1. Those 3 ingredients, combined in different ways, produced every hadron in the zoo. Think of it like primary colors. Red, blue, and yellow are 3 primaries, and every color you can see is a combination of them in specific proportions. The color wheel is not a random collection of hues. It is a structured space generated by 3 fundamentals. The particle zoo had the same character. Every hadron was a combination of quarks in specific proportions, and the geometric patterns of the Eightfold Way were simply the natural consequence of having 3 building blocks, whose properties combined according to fixed rules. The symmetry was not imposed on the particles, it emerged from their composition. The proton was 2 up quarks and 1 down quark. The neutron was 1 up quark and 2 down quarks. The pion was a quark paired with an anti-quark. And the lambda, the particle whose anomalous behavior had started this entire chain of reasoning, was 1 up quark, 1 down quark, and 1 strange quark. That strange quark was everything. It was the source of the lambda's strangeness value of -1. It was the reason the lambda could only be produced alongside a kaon, because producing a strange quark required simultaneously producing a strange antiquark to keep the strangeness total at 0. And it was the reason the lambda lived so much longer than the strong force predicted, because the strange quark could only change its identity through the weak force. Every anomaly the lambda had presented since 1947 dissolved into that one ingredient. One strange quark sitting inside a 3-quark combination, carrying a property that the strong force respected absolutely, and the weak force could slowly dissolve. The lambda was not a mystery anymore. It was a very straightforward consequence of its own composition. The mystery had simply been that nobody knew it had a composition until the mathematics of the Eightfold Way made the existence of quarks unavoidable. But quarks came with their own immediate problem. If the lambda and the proton and every other hadron were made of quarks, where were the quarks? Why had nobody ever seen one on its own? The question of where the quarks were hiding would eventually lead to one of the deepest ideas in all of physics, the mechanism that permanently confines quarks inside hadrons and prevents them from ever appearing alone. That belongs to a separate descent entirely. What matters here is what the quark model did to the lambda specifically, because the lambda is where the explanation lands with the most satisfying completeness. Go back to 1947, a V-shaped track in a cloud chamber in Manchester. A particle that appeared from nowhere, travelled in silence, and split into two. For nearly a decade, that particle resisted every attempt to place it in a coherent framework. It lived too long. It was produced too readily. It never appeared alone. Each of those anomalies had been given a name: strangeness, associated production, weak decay. But names are not explanations. They are placeholders for explanations. What the quark model provided, for the first time, was not a name but a mechanism, a physical picture of what was actually happening inside the lambda that made every one of its behaviors not just describable, but inevitable. The lambda contains one up quark, one down quark, and one strange quark. The strange quark carries strangeness -1, and that strangeness is as fundamental to the strange quark as electric charge is to the electron. It is not a property that can be removed or modified without changing what the particle is. The strong force, which governs the interactions between quarks inside hadrons, treats strangeness as a conserved quantity because it has no mechanism for changing quark flavor. It can push quarks around, exchange gluons between them, hold them together in color-neutral combinations, but it cannot turn a strange quark into an up quark or a down quark. Flavor is invisible to the strong force. It passes right through it. What is most striking about this is that the strong force is by far the most powerful force in nature. It holds atomic nuclei together against the electromagnetic repulsion of positively charged protons, packed into an almost unimaginably small space. It is not a force you would expect to be blocked by anything, and yet here it is, completely unable to complete a decay, not because something overpowers it, but because it simply cannot see the relevant property. The strong force is blind to quark flavor, the way a powerful magnet is useless for picking up wood. The power is real. The tool is just wrong for the job. The weak force, by contrast, is the only force that can change quark flavor. It can turn a strange quark into an up quark, absorbing the strangeness in the process, and it does so through the exchange of a W boson. That flavor change is precisely what the lambda decay requires. The strange quark inside the lambda converts to an up quark, the strangeness disappears, and the 3 quarks rearrange themselves into a proton. A pion is emitted to carry away the excess energy, and conserve the other relevant quantum numbers. The decay is complete, but because the weak force is slow, because the W boson is massive and the interaction it mediates is rare, the whole process takes about 1/10 of a nanosecond, 100 billion times longer than the strong force would have taken, if only it could have acted at all. What the Quark model revealed is that the lambda's strangeness was never really a property of the lambda as a whole. It was a property of one of its three constituents, inherited by the composite particle from its ingredients, the way a cake inherits its sweetness from the sugar inside it, rather than from anything about the shape or size of the cake itself. The lambda was strange because it contained a strange quark. The kaon was strange because it contained a strange quark or anti-quark. The strangeness conservation law that had seemed so abstract and formal when Gell-Mann first wrote it down in 1953 was simply the statement that the strong force cannot change quark flavor, expressed at the level of composite particles before anyone knew composite particles existed. The rule came before the explanation. The accounting worked perfectly for a decade before anyone understood what was being counted. That gap between a working rule and a physical mechanism is one of the most revealing features of how understanding actually advances. Nature hands you the pattern first. The reason follows later, if you keep pushing. The Quark model resolved the lambda, but in doing so, it opened a door onto a problem that had nothing to do with the lambda directly, and everything to do with how the weak force behaves when it changes quark flavor. The weak force could turn a strange quark into an up quark. That much was established. But the mathematics of how it did so produced a prediction that did not match the data, and the mismatch was not small. It was large enough to be embarrassing, and precise enough to be informative. The problem was this: if the weak force can change a strange quark into an up quark, then certain processes involving strange particles should occur at measurable rates. Specifically, a neutral kaon should be able to decay into a muon and an anti-muon at a rate that the theory could calculate precisely. When physicists calculated that rate using the Quark model as it stood in the late 1960s, the number that came out was far larger than what experiments were measuring. The decay was happening, but far less often than the theory predicted. Something was suppressing it. Something was cancelling out most of the contribution the theory was calculating, leaving only a small residual that matched what was actually observed. Think of it like two people pushing a revolving door from opposite sides at almost exactly the same strength. From the outside, the door barely moves, not because nothing is happening, but because two large forces are almost perfectly cancelling each other out. The net effect is small, not because the individual contributions are small, but because they are nearly equal and opposite. The kaon decay rate had that character. The observed rate was tiny, not because the weak force was inactive, but because something was producing a contribution that nearly cancelled the one already in the calculation. In 1970, Sheldon Glashow, John Iliopoulos, and Luciano Maiani identified what that something had to be. Their argument was elegant and precise. If a fourth quark existed, a quark with charge plus 2/3 like the up quark but heavier, and carrying a new quantum number they called charm, then its contribution to the kaon decay calculation would nearly cancel the contribution from the up quark. The cancellation would not be perfect, which was correct, because the observed rate was small but not zero. It would be approximate, suppressed by the mass difference between the up quark and the charm quark, leaving a residual rate that matched the experimental measurement. The GIM mechanism, named for the three physicists who proposed it, required charm to exist before charm had been seen in any detector anywhere. What is worth pausing on here is the chain that produced this prediction. It began with a V-shaped track in a cloud chamber in 1947. That track led to Strangeness. Strangeness led to the Eightfold Way. The Eightfold Way led to Quarks. Quarks led to the weak force flavor-changing mechanism. And the flavor-changing mechanism, when examined carefully enough, demanded a fourth quark that nobody had been looking for and that no experiment had yet produced. The Lambda had not just forced a reorganization of the known particle inventory. It had forced the prediction of something entirely new, something that extended the inventory beyond what any observation had yet required. The charm quark was not a particle anyone had gone looking for on experimental grounds. It was a particle the mathematics insisted had to exist, or the kaon decay rate would be wrong. And the kaon decay rate was not wrong, which meant charm was not wrong either. It was out there, waiting to be found at an energy scale current accelerators had not yet reached. The question was how long it would take to reach it. The answer turned out to be 4 years. In November 1974, 2 experimental teams on opposite sides of the United States announced the discovery of the same particle on the same day without having coordinated their search. Burton Richter's team at the Stanford Linear Accelerator Center in California and Samuel Ting's team at Brookhaven National Laboratory in New York had both been running experiments at different energies using completely different detection methods, and both had found a sharp spike in their data at the same mass, around 3097 mega-electron volts, a region where no known particle had any business producing such a clean and narrow signal. A sharp spike in a particle physics experiment is not a subtle result. Most particles, when they decay, produce broad, smeared signals in a detector because their lifetimes are so short that the uncertainty principle blurs their mass into a range of values. The sharper the spike, the longer the lifetime relative to the strong force timescale, and the spike both teams found was extraordinarily sharp. Whatever this particle was, it lived far longer than a strongly decaying particle had any right to. It was, in that sense, instantly familiar to anyone who had been paying attention to the Lambda problem for the previous 2 decades. Here was another particle living too long. Here was another particle whose lifetime was being protected by something the strong force could not override. The explanation arrived quickly. The new particle was a bound state of a charm quark and a charm antiquark. It was called the J particle by Ting's group and the Psi particle by Richter's group, and it has been called the J-Psi ever since in a compromise that physics has lived with comfortably enough. Its long lifetime was immediately understood as a consequence of a rule analogous to strangeness conservation. A charm quark and a charm antiquark bound together carry a net charm of 0, but decaying into particles without charm quarks requires the weak force to change the flavor, and the weak force is slow. The same mechanism that protected the Lambda was protecting the J. The discovery hit the physics community with a force that is difficult to overstate. It was not just that a new particle had been found. New particles had been found regularly since the 1950s. What made November 1974 different was what the J-Psi confirmed. The GIM mechanism had predicted that charm must exist. The J-Psi was charm, sitting exactly where the mechanism required it to sit, with exactly the properties the Quark model predicted a charm-anti-charm bound state would have. The prediction had been on the table for 4 years. The experimental confirmation arrived and matched it without deviation. This is what distinguishes a physical theory from a descriptive framework. A descriptive framework organizes what is already known. A physical theory reaches beyond the known data and correctly describes what has not yet been seen. The Quark model, combined with a GIM mechanism, had done exactly that. It had predicted a new quark flavor from the behavior of strange particles, and that prediction had been confirmed by 2 independent experiments using two different methods arriving at the same answer on the same day. The Quark model was not bookkeeping, it was physics. The hadrons were genuinely composite, the quarks were genuinely real, and the chain that had produced this confirmation stretched all the way back to a V-shaped track in a cloud chamber in Manchester in 1947. The particle zoo that had seemed so chaotic in the 1950s now had a foundation. 4 quarks, up, down, strange, and charm, combining according to fixed rules, producing every hadron that had ever been observed. The inventory was not random, it was structured all the way down, and that structure, it would turn out, was not yet complete. 4 quarks organized the known hadron spectrum cleanly. Up, down, strange, and charm accounted for every particle in the zoo, explained every anomaly that had accumulated since 1947, and produced predictions that matched experiment with a precision that left no serious room for doubt. It would have been reasonable at that point to hope the inventory was complete. 4 quarks, 4 leptons, the electron and its neutrino, and the muon and its neutrino, a tidy parallel structure between the two sectors of matter. The universe had been generous enough to organize itself into 2 neat generations. Perhaps it stopped there. It did not stop there. In 1977, Leon Liederman's team at Fermilab discovered a new particle called the upsilon, a bound state of a new heavy quark and its antiquark, at a mass nearly 10 times higher than the J-psi. The new quark was called bottom. Its existence meant a 5th quark, and a 5th quark sitting alone without a partner was theoretically uncomfortable in the same way a single glove is, practically useless. The mathematical structure that had made the GIM mechanism work, the structure that required quarks to come in pairs of specific types to cancel unwanted quantum corrections, demanded a 6th quark to partner the bottom. That 6th quark was called top, and it was found in 1995 at Fermilab after a search that required building one of the most powerful accelerators of the 20th century, specifically to reach the energy scale where the top quark lived. The top quark is remarkable on its own terms and worth pausing on. It is by far the heaviest known fundamental particle, weighing about as much as an atom of tungsten, a fact that sits uncomfortably without explanation, in the same way the Lambda's lifetime once sat uncomfortably without explanation. Something is giving the top quark that mass. The Higgs mechanism provides the framework for how, but why the top couples to the Higgs field so much more strongly than every other quark remains an open question. The Higgs mechanism provides the framework for how, but why the top couples to the Higgs field so much more strongly than every other quark remains an open question. The pattern of masses across the 3 generations of matter is one of the deepest unsolved problems in particle physics, and it has exactly the same character as the Lambda problem did in 1950. The measurements are precise, the explanation is absent. Something is waiting to be found. What strikes me about this is the familiarity of it. The top quark's unexplained mass has exactly the same shape as the Lambda's unexplained lifetime did in 1950. A precise measurement sitting without a mechanism. Physics has been here before and it knows what that feeling means. It means there is another layer. With 6 quarks established, the structure of matter resolved into 3 complete generations. The first generation contained the up and down quarks, the electron and the electron neutrino. These were the constituents of ordinary stable matter, the ingredients of every atom in every object that has ever existed at room temperature. The second generation contained the charm and strange quarks, the muon and the muon neutrino. The third generation contained the top and bottom quarks, the tau and the tau neutrino. Each generation was a complete copy of the one before it, identical in structure and force interactions, differing only in mass, with each successive generation dramatically heavier than the previous one. The Lambda sits at the entry point of this entire architecture. It was the first particle discovered that belonged to a generation beyond the first sign that the universe had not stopped at the minimal set of ingredients needed to build stable matter. The strange quark it contains is a second-generation quark, and the Lambda's anomalous behavior was the first experimental evidence that a second generation existed at all. Every discovery that followed, the Eightfold Way, the Quark model, the GIM Mechanism, Charm, bottom, top, the full three-generation structure of the Standard Model, can be traced in a direct unbroken line back to that single anomalous particle, and the questions its behavior forced physicists to ask. The Standard Model as it stands today describes 3 generations of quarks and 3 generations of leptons, organized into a parallel structure whose mathematical consistency requires the generations to match between the 2 sectors. It accommodates all of this with extraordinary precision. What it does not do is explain why there are 3 generations rather than 2 or 4, or why the masses follow the pattern they do, or what determines the specific values that distinguish one generation from the next. Those questions are open. They have the same shape the Lambda problem had in 1950. The measurements are clear, the mechanism is hidden, and somewhere in that gap, the next layer of understanding is waiting. In 1947, 2 physicists in Manchester developed a cloud chamber photograph and found a shape that did not belong. A V. Clean, reproducible, pointing back to a single neutral parent with a definite mass and a specific set of decay products. The particle was real. The framework that should have explained it had nothing to say. And the questions that V-shaped track forced into existence did not stop until they had restructured the entire understanding of what matter is made of. Follow the chain from the beginning, and the length of it is difficult to take in all at once. The V-shaped track forced the lifetime measurement. The lifetime measurement revealed a particle living 100 billion times longer than the strong force predicted. That gap demanded an explanation. The explanation required a new conserved quantity. The new conserved quantity, strangeness, made the paired production of the Lambda and the kaon inevitable, and made the long lifetime a direct consequence of the strong force's own accounting rules. Strangeness did not solve the problem so much as it gave the problem a precise shape, sharp enough that the next step became visible. The next step was the particle zoo. Accelerators filled the inventory with dozens of strange particles through the 1950s, each one carrying strangeness values that clustered into patterns too regular to be accidental. Those patterns demanded an organizing principle. The organizing principle, SU3 symmetry, arranged the hadrons into geometric families with a precision that went beyond description into prediction. The prediction was the omega minus, a particle specified in advance with a specific mass, charge, and strangeness, found in 1964 exactly where the symmetry said it would be. A symmetry that predicts undiscovered particles is not a filing system. It is pointing at physical substructure. The substructure was quarks, 3 of them, up, down, and strange, whose properties combined according to fixed rules to produce every hadron in the zoo. The Lambda was 1 up quark, 1 down quark, 1 strange quark, and every anomaly it had ever presented dissolved immediately into that composition. The long lifetime was the strange quark being unable to change flavor through the strong force. The paired production was the strong force conserving strangeness by producing strange quarks only alongside strange anti-quarks, The decay products were the strange quark converting to an up quark through the weak force, and the three quarks rearranging into a proton. Nothing exotic, nothing arbitrary, everything inevitable once the composition was known. But the quark model did not stop at three quarks. The mathematics of how the weak force changes quark flavor produced a prediction that did not match the data, and resolving that mismatch required a fourth quark. Charm predicted in 1970 and confirmed in 1974 when two independent experiments found the J psi on the same day. Charm forced a fifth quark. Bottom, discovered in 1977. Bottom forced a sixth. Top, found in 1995. 6 quarks organized into 3 generations, each one a complete structural copy of the one before it, at a higher mass scale, parallel in every detail to 3 generations of leptons on the other side of the matter inventory. The standard model, the most precisely tested physical theory ever constructed, took the shape it has today. All of it is traceable to one particle, not because the Lambda was the most fundamental object in the chain, or the most mathematically sophisticated, or the most experimentally dramatic, but because it was the first crack. It was the first place where the existing framework met a measurement it could not accommodate, where the gap between prediction and observation was large enough and clean enough and reproducible enough that it could not be explained away. The Lambda did not fit, and physics, when confronted with something that does not fit, has only one honest response. It has to find out why. The why led to strangeness. Strangeness led to quarks. Quarks led to charm. Charm led to 3 generations. 3 generations led to the standard model. And the standard model, for all its precision, still carries open questions whose shape is recognizable. Masses that are measured but not derived. Generations that are counted but not explained. Gaps between what the theory accommodates and what it understands. The Lambda did not just rebuild physics once, it left behind a template for how physics gets rebuilt, an anomaly precise enough to be undeniable, a gap that demands to be closed, and somewhere on the other side of that gap, a layer of structure that nobody has seen yet, but that the pattern is already pointing toward. The V-shaped track in the cloud chamber was not the end of anything. It was the first domino.